Okay, it's time for motion in 2 and 3 dimensions. Most of the time we'll be working with 2 dimensions, but we need to know how to do 3 also. The reason we just covered chapter 3 is because that was all in vectors, if you recall. And to describe motion in 2 or 3 dimensions, we are going to have to use vectors. If we're describing position or displacement, it'll be in vector form. If we have velocity or acceleration, it'll be in vector form. And when we get to forces and the accelerations they cause, those forces will be in vector form also. Okay, so I'm going to go ahead here and start out with the graph. Okay, let's call this our x-axis corresponds to I, y corresponds to j, and this will be our positive z-axis out here. Let's say we have some vector, and it's describing some location out here. Alright, there's some mass out there, there's something we can describe. Well, we need to break this into components. We can say this has some component in the I or negative I direction. So let me finish the drawing, it'll make a little bit more sense. We can say, and I'll put numbers to this also, that it's a little bit above the y-axis, so it's going to have some y component. This is our I, this would be our j component, and it looks like it comes out here along the z-axis, like so. And we would point our z vector, or in the k direction, like that. So when you add the I to the j to the k vector, the resultant vector is this one right here. So what does that mean? It means that if we wanted to describe its position, it would be a vector r, which we'll call the position vector. It usually goes from some reference point. In this case, we'll use the origin. We can put the origin there. We can call anything our reference point. But we have components in the I direction. So some magnitude of x in the I direction, some magnitude of y in the j direction, and some magnitude of z in the k direction. Alright, that is how we describe a vector. Let's give this some numbers. Let's say that it goes over negative 3i, and it's going up, this is from your book too, a positive 2 meters in the j direction, and out in the k direction we have a 5. Oh, that looks like kilometers. Let's throw the meter inside. So positive 2 meters in the j direction. And a negative 3 meters in the k direction. Okay, well, we can literally put those numbers right into the formula for our position vector and describe the location of the particle. So, right now we're doing particle motion. You get into your next physics class, you'll be looking at wave motion, but for now we're working with particles, and soon we'll have some mass m once we start dealing with forces. So if I take that x component, I get a negative 3, and that's in the I direction. If I take the y component, I get a positive 2, and that is in the J direction. And what else? I need another color. The Z, or the K direction. The Z value is 5 meters, and that's in our K direction, K hat. Okay. I just lost my thought. I had something good to say. Notice we could always find the magnitude of this vector. The angle's a little bit tricky. It's got 2 angles describing it, but we could always find the magnitude of something with 3 components still very easily. It's just Pythagorean theorem for 3 things. So we'd have a -3 squared plus 2 squared plus 5 squared. Alright. After we originally learned about position, so if this is a position vector, what was the next thing? Well, the next thing we learned about in 1 dimension was displacement. If you remember what displacement is, it's equal to our, in this case, it's going to be delta R. It's change in position, right? So before we had x2 minus x1, and that was equal to some delta x, or the displacement in the x direction. Now we have delta R. So we'll look at the whole vector at 2, and then subtract the whole vector at 1. It could still be in 1 dimension. It could still only be on the x-axis. This is a more general definition. So we need to know that. And if we had some vector, let's say if R1 points to some x1 in the I direction, plus, that's a meter, some y1 in the j direction, plus some z1 in the k direction, and we had some R2 equal to an x2 in the I, and a y2 in the j, and a z2 in the k direction. Well, I can throw those in my displacement formula, and we get a delta R. Subtracting 2 vectors will always give us a vector, so we're just subtracting like components. R2 minus R1, that gives us x2 minus x1, and that'll be in the I direction. Y2 minus y1 will be our next component, and that's in the j direction. And then we have a z2 minus z1. And all of that's in the k direction. If we didn't have a z coordinate, just get rid of it. We don't have it. So this definition still holds for 1 or 2 directions or 3 directions. I and j, or I and k, or j and k, or all 3. Okay, we can simplify this a little bit and just say delta R is equal to delta x in the I direction. And it should throw some unit on here, right? Plus some delta y in the j, plus some delta z in the k direction. And that would have some whole unit of meters.